Let's take a look at problem 8.80 that asks us to calculate the wavelength needed to break a bond. The problem sets it up by saying a mixture of hydrogen and chlorine is stable, but a bright flash of light passing through can cause the mixture to explode. The light causes the Cl2 molecules to split into Cl2 atoms, which are highly reactive. What wavelength of light is necessary to cause the chlorine molecules to split? So the first part of the question gives us this background information to understand what is going on. And the question we're trying to answer is, what is the wavelength, or lambda, of light necessary to cause the chlorine molecules to split? Now, they also give us the bond energy of the chlorine molecules as a 242.6 kilojoules per mole. Now, this per mole caught my attention right here because we're talking about the wavelength needed to break one bond, but this is per mole of bond. So per mole of chlorine, sorry. So what I need to do is use Avogadro's number and cancel out moles and figure out what is the energy to break the bond of one molecule. So I'm going to divide 242.6 kilojoules by Avogadro's number. Now, one thing I want to draw to your attention, some of you, the way you enter into your calculators the exponential notation, you may find you don't get the right answer unless you put a parenthesis around the entire formula. So dividing this number, I get 4.029 times 10 to the negative 20 seconds kilojoules now per molecule. Now, I plan on using an equation that requires me to work in joules, so I will multiply this number by 1,000 to get 4.029 times 10 to the negative 19 joules per molecule. Now, I know from a previous chapter that the energy of light, one formula, could be that it's equal to Planck's constant times the speed of light divided by wavelength. Now, so if I know that to be true, I can rearrange this equation and solve for wavelength. So I know wavelength will equal Planck's constant times the speed of light divided by the energy. So let's plug that in, and I get wavelength equals. I get wavelength equals Planck's constant, 626 times 10 to the negative 34 joules times seconds, times the speed of light, divided by the energy that I calculated up above. Looking at your units, you'll see that everything will cancel except for the meters. And the answer that you get is 4.934 times 10 to the negative 7 meters. Now, oftentimes the wavelength is written in nanometers. So if and nano is 10 to the negative 9 meters. So if I move my decimal 2 places to the right, I could convert this into nanometers, and I get 493.4 nanometers, because that would make it 10 to the negative 9. Now this also asks me, well, this doesn't ask me what color this light is, but this is in the visible spectrum. And if you look in the visible spectrum, you would see that this light would be green.